The p-block elements. Introduction. The properties of p-block elements, like that of others, are greatly influenced by atomic sizes, ionization enthalpy, electron gain enthalpy, and electronegativity. The absence of d orbitals in second period and presence of d and or f orbitals in heavier metals have significant effects on the properties of elements. In addition, the presence of all the three types of elements, metals, metalloids and non-metals, bring diversification in chemistry of these elements. Group 15 elements. Group 15 includes nitrogen, phosphorus, arsenic, antimony and bismuth. Nitrogen and phosphorus are non-metals, arsenic and antimony metalloids, and bismuth is a typical metal. Molecular nitrogen comprises 78% by volume of the atmosphere. Phosphorus occurs in minerals of the apatite family. Arsenic, antimony, and bismuth are found mainly as sulfide minerals. The important atomic and physical properties of this group elements, along with their electronic configurations. Chemical properties. Nitrogen differs from the rest of the members of this group due to its small size, high electronegativity, high ionization enthalpy, and non-availability of d orbital. Reaction of group 15 elements with hydrogen, oxygen, halogens, and metals. Dinitrogen. Dinitrogen is produced commercially by the liquefaction and fractional distillation of air. Liquid dinitrogen distills out first, leaving behind liquid oxygen. In the laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with sodium nitrite. Small amounts of NO and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through aqueous sulphuric acid containing potassium dichromate. Very pure nitrogen can be obtained by the thermal decomposition of sodium or barium acid. Physical properties. Dinitrogen is a colorless, odorless, tasteless and non-toxic gas. Nitrogen atom has two stable isotopes, 14N and 15N. It has a very low solubility in water and low freezing and boiling points. The physical properties of nitrogen. Chemical properties. It combines with hydrogen at about 773 K in the presence of a catalyst to form ammonia. Dinitrogen combines with dioxygen only at very high temperature to form nitric oxide, NO. Preparation of ammonia. Haber's process. Ammonia is prepared in large amounts by its synthesis from elementary nitrogen and hydrogen. In practice, a temperature of 725 to 775 K, 200 to 300 atmosphere pressure, and a solid comprising of finely divided ion as catalyst and molybdenum as promoter are used. Ions as catalyst with small amounts of a mixture of potassium and aluminum oxides as promoter can be used as an alternative. Pure and dry N2 and H2 mixture in 1:3 ratio by volume is compressed to 200 to 300 atmosphere pressure. Then it passes into a catalytic chamber. The gases, partially heated in the heat exchanger, react in the presence of the catalyst at 725 to 775 K in the chamber. Ammonia is formed to the extent of about 10% in the reaction. It is separated from the unreacted N2 and H2 by condensation in the condenser. Properties of ammonia. Ammonia is a colorless gas with a pungent odor. In the solid and liquid states, it is associated through hydrogen bonds, as in the case of water, and that accounts for its higher melting and boiling points than expected on the basis of its molecular mass. The ammonia molecule is trigonal pyramidal with the nitrogen atom at the apex. It has 3 bond pairs and 1 lone pair of electrons as shown in the structure. Ammonia gas is highly soluble in water. Oxides of nitrogen. Nitrogen forms a number of oxides in different oxidation states. The names, formulas, preparation, and physical appearance of these oxides are given in the table. Lewis dot main resonance structures and bond parameters of oxides are given in table. Preparation of nitric acid. In the laboratory, nitric acid is prepared by heating KNO3 or NaNO3 and concentrated H2SO4 in a glass retort. On a large scale, it is prepared mainly by Ostwald's process. This method is based upon catalytic oxidation of NH3 by atmospheric oxygen. Physical properties. It is a colorless liquid. Laboratory-grade nitric acid contains 68% of the HNO3 by mass and has a specific gravity of 1.504. In the gaseous state, HNO3 exists as a planar molecule with the structure as shown. Chemical properties. Concentrated nitric acid is a strong oxidizing agent and attacks most metals except noble metals such as gold and platinum. The products of oxidation depend upon the concentration of the acid, temperature, and the nature of the material undergoing oxidation. Brown ring test. The familiar brown ring test for nitrates depends on the ability of Fe2 positive to reduce nitrates to nitric oxide, which reacts with Fe2 positive to form a brown-colored complex. The test is usually carried out by adding dilute ferrous sulfate solution to an aqueous solution containing nitrate ion and then carefully adding concentrated sulfuric acid along the sides of the test tube. A brown ring at the interface between the solution and sulfuric acid layers indicates the presence of nitrate in solution. Phosphorus allotropic forms. White phosphorus is a translucent white waxy solid. It is poisonous, insoluble in water but soluble in carbon disulfide and glows in dark. It dissolves in boiling NaOH solution in an inert atmosphere giving pH 3. It consists of discrete tetrahedral P4 molecule. Red phosphorus. Red phosphorus is obtained by heating white phosphorus at 573 K in an inert atmosphere for several days. When red phosphorus is heated under high pressure, a series of phases of black phosphorus is formed. Red phosphorus possesses iron-gray luster. It is odorless, non-poisonous and insoluble in water as well as in carbon disulfide. Chemically, red phosphorus is much less reactive than white phosphorus. It does not glow in the dark. It is polymeric, consisting of chains of P4 tetrahedral linked together as shown. Black phosphorus. Black phosphorus has two forms, alpha black phosphorus and beta black phosphorus. Alpha black phosphorus is formed when red phosphorus is heated in a sealed tube at 803 K. It can be sublimed in air and has opaque monoclinic or rhombohedral crystals. It does not oxidize in air. Beta black phosphorus is prepared by heating white phosphorus at 473 K under high pressure. It does not burn in up to 673 K. Preparation of phosphine. Phosphine is prepared by the action of calcium phosphide with water or dilute HCl. In the laboratory, it is prepared by heating white phosphorus with concentrated NaOH solution in an inert atmosphere of CO2. When pure, it is non-inflammable but becomes inflammable owing to the presence of P4 vapor. To purify it from the impurities, it is absorbed in HI to form phosphonium iodide, which on treating with KOH gives off phosphine. Phosphorus trichloride. It is obtained by passing dry chlorine over heated white phosphorus. It is also obtained by the action of thionyl chloride with white phosphorus. It has a pyramidal shape as shown in which phosphorus is sp3 hybridized. Phosphorus pentachloride. Phosphorus pentachloride is prepared by the reaction of white phosphorus with excess of dry chlorine. It can also be prepared by the action of SO2Cl2 on phosphorus. In the gaseous and liquid phases, it has a triagonal bipyramidal structure as shown. Orthophosphorus acid. H3PO3. The basicity of the acid is 2. It gives two series of salts, namely primary phosphates H2PO3 and secondary phosphides HPO3 to the power of -2. Metaphosphorus acid HPO2. The basicity of this acid is 1. Normally, this exists as a cyclic compound. Only monomer's structure is shown here. Hypophosphorus acid H3PO2. The basicity of this acid is 1. Its salts are known as hypophosphides H2PO2. This is a colorless acid. Orthophosphoric acid H3PO4. This is tribasic acid. It forms 3 series of salts. These are dihydrogen phosphates, example NaH2PO4, monohydrogen phosphates, example Na2HPO4, and normal phosphates, example Na3PO4. The acid loses water steadily on heating. Its structure is represented in the figure shown here. Metaphosphoric acid HPO3. The acid is obtained by heating H3PO4 or H4P2O7 at red heat. It is known as glacial phosphoric acid as it is a transparent, glassy solid. Its salts are known as metaphosphates. There is no evidence for the existence of free monophosphate PO3 ions, but the monophosphates form a family of ring compounds like triphosphates, tetraphosphates, or polyphosphates. Pyrophosphoric acid H4P2O7. Pyrophoric acid is a tetrabasic acid. Its normal salts, example M4P2O7, where M is monovalent metal, and Ca2P2O7 used in fluoride toothpastes, and dihydrogen salts M2H2P2O7, example Na2H2P2O7 used in making bread, are the common types of salts of the acid. The structure of the acid is written as shown. Hypophosphoric acid H4P2O6. The structure of the acid is shown above. Peroxyphosphoric acid H3PO5. This tribasic acid is structurally represented as shown above. Group 16 elements. Oxygen is the first member of the group 6A, and sulfur is the second member of this group. Other members of this group are selenium, tellurium, and polonium. Members of group 6A have 6 electrons in their valence shell. They generally show a valency of -2. Oxygen shows a fixed valency of 2. White sulfur shows variable valencies of 2, +4, and +6 also. Preparation of oxygen from oxides. Generally, oxides do not decompose when heated. However, oxides of mercury and silver decompose completely to yield their respective metal and oxygen. The higher oxides of lead, namely lead oxide and trilead tetroxide, when heated, decompose to yield the lower oxide and oxygen. Laboratory preparation of oxygen. For the laboratory preparation of oxygen from any of the compounds like lead dioxide, trilead tetroxide, potassium nitrate, sodium nitrate, potassium chlorate, or potassium permanganate, the arrangement of apparatus is shown. Oxygen is usually collected over water because the solubility of the gas in water is not high. If the gas is needed dry, then it can be passed through a drying agent like anhydrous calcium chloride or quicklime or concentrated sulphuric acid and then collected over mercury. Preparation of ozone. Ozone is prepared by passing silent electric discharge through cold, dry oxygen. The reaction is given above. This is an endothermic change. According to Le Chatelier principle, energy must be supplied to produce ozone. The instrument used for this is known as ozonizer. 2 kinds of ozonizers are commonly used in the laboratory: a Siemens ozonizer and Brody's ozonizer. Oxidation reactions. Ozone is next to fluoride in its oxidizing capacity. The oxidation reactions of O3 can be divided into two categories. 1. Reactions in which oxygen is evolved or 1 oxygen per ozone molecule is utilized. No oxygen is evolved or all the oxygen atoms in ozone are consumed. Uses of ozone. The uses of ozone are shown above. Sulfur. Sulfur forms numerous allotropes, of which the yellow rhombic and monoclinic forms are the most important. Both rhombic and monoclinic sulfur have S8 molecules. These S8 molecules are packed to give different crystal structures. Oxacids of sulphur. Sulfur forms a number of oxacids such as H2SO3, H2S2O3, H2S2O4, H2SX06, H2SO4, H2S2O7, H2SO5. Some of these acids are unstable and cannot be isolated. Structures of some important oxoacids are shown in figure. Sulphuric acid. The key step in the manufacture of sulphuric acid is the catalytic oxidation of SO2 with O2 to give SO3 in the presence of V2O5. The reaction is exothermic, reversible, and the forward reaction leads to a decrease in volume. The plant is operated at a pressure of 2 bar and a temperature of 720 K. The SO3 gas from the catalytic converter is absorbed in concentrated H2SO4 to produce oleum. Dilution of oleum with water gives H2SO4 of the desired concentration. In the industry, 2 steps are carried out simultaneously to make the process a continuous one and also to reduce the cost. The sulphuric acid obtained by contact process is 96 to 98% pure. Properties. Sulphuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84 at 298 K. The acid freezes at 283 K and boils at 611 K. It dissolves in water with the evolution of a large quantity of heat. Hot concentrated sulphuric acid is a moderately strong oxidizing agent. In this respect, it is intermediate between phosphoric and nitric acids. Both metals and non-metals are oxidized by concentrated sulphuric acid, which is reduced to SO2. Group 17 elements. Chlorine is placed second after fluorine. Group 17 elements. Other members of this group are fluorine, bromine, iodine, and astatine. Members of this group are called halogens, meaning salt producers. Atoms of halogens have 7 electrons in their valence shell, thus show -1 valency. Halogens may be solid, liquid, or gas. Preparation of fluorine. The Whitelaw-Gray method. In this method, electrolysis is carried out in an electrically heated copper cell. The electrolyte is fused potassium hydrogen fluoride 1:2, Kf:/HF. The reactions shown above occurs. The copper vessel serves as cathode also. Anode is made of graphite. The anode is surrounded by a copper diaphragm perforated at the bottom. The diaphragm prevents the mixing of H2 and F2, which react explosively if they come into contact. F2, liberated at the anode, is passed through the U-tube containing sodium fluoride. Hydrogen fluoride vapors accompanying fluorine as impurity are removed by NaF. H2 is liberated at the cathode. The corrosion of the cell by the action of F2 is prevented by Teflon coating given to various parts of the cell. The fluorine obtained in this method is almost pure with traces of the HF present in it. Chemical properties. Fluorine is a very reactive element and therefore reacts with a large number of substances like water, alkalis, metals, nonmetals, halide, and inert gases. Uses of fluorine. Fluorine is used in several ways, mostly in the form of its compounds. Abnormal behavior of fluorine. Fluorine differs considerably from other halogens. The reasons are: fluorine has small size, highest electronegativity, no d orbitals available in its valency shell, low dissociation energy for FF bond, and 2 electrons only in the penultimate shell, while other halogens have 8 electrons. The abnormal characteristics can be summarized as shown above. Preparation of chlorine. Chlorine can be prepared in the laboratory by oxidation of hydrochloric acid with manganese dioxide. Nowadays, industrially, chlorine is prepared by Downs process and electrolysis of brine solution using Nelson cell. In the Nelson's process, brine solution is electrolyzed. The reactions shown above take place. In the electrolytic cell, if the products come into contact with one another, other side reactions are likely to take place. Therefore, Nelson's cell arrangements are such that NaOH and Cl2 do not come together. Preparation of chlorine. In the Nelson's process, a perforated steel U-tube lined inside with asbestos is used as cathode as shown. The U-tube is suspended in outer iron tank. Brine solution is taken inside U-tube. A carbon rod, anode, is suspended into the brine solution from the roof of the tank. The cathode and the anode are separated by the asbestos lining present inside the U-tube. Chlorine liberated during the electrolysis is led out from the anode. Chemical properties. Chlorine dissolves in water. The solution is known as chlorine water, and a fresh solution contains HCl and HOCl. Cold, dilute alkalis react with chlorine and produce chlorides and hypochloriates. The reaction of chlorine with water and alkalis are shown above. Reaction with metals and nonmetals. Active metals combine with Cl2 to give the respective metal chlorides. If a metal can form more than one chloride, that metal chloride in which the metal is in its highest stable oxidation state is produced by direct union of elements. H2, P4 and S directly unite with chlorine and give chloride. The reactions are written as shown above. Reaction with hydrocarbons. Saturated hydrocarbons undergo substitution reactions in sunlight or UV radiation. In these reactions, all the hydrogen atoms are substituted by chlorine atoms successively. Unsaturated hydrocarbons like alkenes, alkynes readily undergo addition reactions. In the presence of Lewis acids like AlCl3, FeCl3, etc., chlorine reacts with benzene to give chlorobenzene. Oxidation by chlorine. Chlorine is a strong oxidizing agent. It oxidizes ferrous chloride to ferric chloride and hydrogen sulfide to sulfur. Moist chlorine oxidizes vegetable coloring matter and bleaches it. Sodium sulfite and thiosulfate are oxidized to sodium sulfate. Uses of chlorine. The uses of chlorine are shown above. Oxyacids of chlorine. The various oxyacids of chlorine are hypochlorous acid, chlorous acid, chloric acid, and perchloric acid. The central element in all these acids is chlorine. The structures of all these acids are based on tetrahedron. The chlorine in all these acids undergoes sp3 hybridization. In the series of oxyacids, HClO, HClO2, HClO3, and HClO4, each acid has a chlorine that is linked to an OH group, and an increasing number of oxygen atoms are bonded to the central chlorine atom. The structure of the acids are represented as shown above. Oxoacids of halogens. Due to high electronegativity and small size, fluorine forms only one oxoacid, HOF, known as fluoric acid or hypofluorous acid. The other halogens form several oxoacids. Most of them cannot be isolated in pure state. They are stable only in aqueous solution or in the form of their salts. The oxoacids of halogens are given in table Interhalogen compounds. When two different halogens react with each other, interhalogen compounds are formed. They can be assigned general compositions as XX, XX3, XX5, and XX7, where X is halogen of larger size and X of smaller size, and X is more electropositive than X. As ratio between radii of X and X increases, the number of atoms per molecule also increases. Thus, iodine fluoride should have maximum number of atoms, as the ratio of radii between I and F should be maximum. Some properties of interhalogen compounds are given in table. Group 18 elements. Group 18 consists of 6 elements: helium, neon, argon, krypton, xenon, and radon. All these are gases and chemically unreactive. They form very few compounds. Because of this, they are termed noble gases. The atomic and physical properties of group 18 elements are given above. Xenon oxygen compounds. XeO3 is a colorless explosive solid and has a pyramidal molecular structure. XeOF4 is a colorless volatile liquid and has a square pyramidal molecular structure. Hydrolysis of XeF4 and XeF6 with water gives XeO3. Partial hydrolysis of XeF6 gives oxyfluorides, XeOF4 and XeO2F2.